Okay, just give me a thumbs up that you guys see me and hear me okay on the board. Everybody's good? All right, here we go. Number one, let's try this one. Okay. All right, so again, these rational functions, they are fractions. So being a fraction and the fact that we don't want to divide by 0, it creates restrictions on the graph. So number one, our first step is always f, d, r. Factor, find your domain, and then you're allowed to reduce it. All right, so if I factor difference of two squares, bottom has a GCF. Now again, don't look to cancel yet. Look to find the bad guys. So go to your denominator. Who's going to make the bottom of this fraction equal 0? That's a number that we would never want to plug into this function. I definitely don't want to plug in 2. X is not allowed to be 2. If I plug in 2, I'll be dividing by 0. So that's the only bad guy. So our domain is going to be from negative infinity to 2 union 2 to positive infinity. That's your domain. All right, now you'd be allowed to go back and reduce it. Unfortunately, we have no like factors on top and bottom, so nothing cancels out. If nothing cancels, that just means down the road, you'll have a VA, but you won't have any holes. No holes. A hole would come from a factor that canceled. All right, so step 2. We want to get those vertical asymptotes, those brick walls that your graph cannot cross and cannot exist at. So if you look at your graph, who's still the bad guy? Who is still in your denominator looking really, really bad? It's 2. So we're going to have a vertical asymptote at the line, x equals 2, because our graph cannot exist there. So put it on the graph. Okay? All right, now, step 3. I want to go after our horizontal asymptote or our oblique asymptote. It cannot have both. It has to have one or the other based off of our HAOA rules. All right, well, if you look, nothing reduced. So look at the beginning. It's a degree 2 over a degree 1. This would be rule number 3. Rule number 3 says that when the numerator's degree is bigger than the denominator's degree, you will have no HA. You will have an oblique asymptote. Because, guys, that's what division is all about. If the top degree is bigger, that means that when you plug these really, really large x values in at the end of the graph, that means the top number is going to be bigger and the bottom number will be smaller. That's division. Big number divided by small number. So we have to actually divide to see what they're actually heading towards becoming. So we're going to take, it's always easier to take the multiplied version, so I don't need the factored version for this. If it had reduced, I may have taken the reduced version and done my long division, but you may have to multiply it back together in that reduced version. All right, so how many times does 2x minus 4 go into x squared minus 9? But guys, you have to placeholder. It's just like synthetic. If you're missing a term, you have to fill in a 0. So x squared plus 0x's and then minus 9. You are going to need that placeholder right there. Okay. When we long divide polynomials, you're taking the first term in this polynomial and seeing how many times it goes to the first term of this polynomial. Or I say to myself, what could I put up here so that when I multiply it with 2x, I get x squared, right? How many times does 2x go into a 1x squared? That's actually 1/2 x times. All right, so 1/2 x times 2x gets me that 1x squared. That's what you want. You want this term to match in the multiplying step. All right, so now we multiply it in. What's 1/2 x times 2x? That's going to be 1x squared. See how they match? If they don't match, you did not put the right term up here. All right, what's 1/2 x times negative 4? That's negative 2x. Now long division says we subtract to see what's left, but you have to pick up that subtraction each time. So x squared, subtract x squared, they cancel. That's what you want. If that doesn't happen, you didn't put the right term up top, like I said. All right, now I'm taking 0x's and I'm subtracting negative 2x's. Subtracting a negative 2 turns to a plus. So 0 plus 2x's is 2x. Then you bring down the minus 9 and you do it all over again. All right, well, first term into first term. How many times does 2x go into a 2x? Or what could I put up here so that when I multiply with 2x, I get a 2x so that they match? a positive 1. All right, so now we multiply it in. What's positive 1 times 2x? It's 2x. See how they match? That means they're going to cancel in that subtraction step. What's 1 times negative 4? Negative 4. Now we subtract, and we see what's left. 2x, take away 2x, cancel. Negative 9, subtract negative 4 turns to a plus, and you're left with negative 5. But guys, that's your remainder. So this would be like minus 5 over the 2x minus 4, because you always write the remainder over who you divided by. But when you're plugging in these really large x values, negative 5 divided by 2 times a million minus 4, guys, this is basically 0. So we drop the remainder. You always drop the remainder. So don't even worry about it. Leave your remainder. And guys, sometimes your remainder is like a mathematical expression, and that's fine. You always drop the remainder. All right, so that means our oblique, our slanted line asymptote, is the line y equals 1/2 x plus 1. So now you have to graph that slanted line as your asymptote. But I do not recommend putting dots, because I don't want you guys to mistake these dots as points that your curve is going to pass through. So I'll just put like little tick marks, little slashes. So 1/2 x plus 1 has a y-intercept at 1 and a slope of 1 over 2. So up 1, right 2, up 1, right 2, up 1, right 2, and just keep creating that slanted asymptote. Down 1, left 2, 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 and so on. So again, I don't want to make it dots because I don't want them to be mistaken as points that my curve is going to pass through. Just put them as little slash marks. Now guys, be very careful, because you may have points that are really, really close to the asymptote, and you want to make sure that you know if it's above or below the asymptote. So try and keep that slanted line perfectly straight. All right, let me pause. Everybody okay? Everybody's good? All right, now, step 4 is probably my least favorite step. We know that our graph is never going to pass a vertical asymptote, but we don't know if it passes over the HA or the OA. It's allowed to pass over an HA or an OA. So we have to check to see if it's going to cross over that asymptote. So now we're going to check to see if it crosses. So in order to do that, you have to take your function. You would take the reduced function. Unfortunately, ours did not reduce, so it doesn't matter which one we take. It doesn't matter if I take the factored version or the multiplied out version that we started with. It doesn't matter because nothing changed, nothing reduced. So sometimes in this step, it's easier to take the multiplied out one because we're going to have to cross multiply. So does x squared minus 9 over 2x minus 4 ever end up equaling this asymptote? So set it equal to it like this. I know that seems weird, but that's what we're going to do. And then we're going to cross multiply to see if these ever become equal. Is there an x value that makes this function equal the oblique asymptote? So if we cross multiply, let's do the first one easy. X squared minus 9 times 1, x squared minus 9. Okay? Equals the other cross product. Guys, this is a FOIL. It's 2 terms times 2 terms. We're going to have to FOIL this out. So 2x times 1/2 x is x squared. 2x times positive 1 is 2x. Negative 4 times positive 1/2 x is negative 2x. And then negative 4 times positive 1 is negative 4. All right, watch what happens. These cancel right away. If I tried to get my x squareds on one side, if I minus them here or minus them there, they would cancel. And I'm left with negative 9 equaling negative 4. You see how all the x's canceled out in the solving? That means when the variables cancel, it's not going to cross. You're going to be left with some false statement, which is good because we don't want to cross. It just complicates things. So that means no cross. Okay, so that means everything is going to stay in their box, if you will. The curve to the left is either going to be up here above this slanted asymptote, or the curve to the left is going to be down here in this like piece of pie shaped. All right, the curve to the right will either be entirely up here, or the curve to the right will be entirely down here. There's no crossing over into the other sections, if you will. All right, after that, we're kind of like home free. Now we're just going to go after some legit points that are on this graph. I have to erase this right now because I need more board space, but I can't move my graph. So I'm going to have to get rid of this. I'm just going to leave that in case anybody was still looking at it. Okay, so now step 5 would be, is there any holes? And a hole can only come from a factor that canceled on top and bottom in that reducing step. Nothing canceled, so there's no holes. Okay, now step 6. Now I'm looking for some legit points like intercepts. What are my x-intercepts? What are my y-intercepts? Remember, there can be more than one x-intercept, but there will only ever be one y-intercept if there's going to be one. All right, to find your x-intercepts, you take, oh, I shouldn't have erased the actual function. All right, you take your function and you set it equal to 0. What are the zeros? What is x going to be to make this function equal 0? So if you take it, and again, if it had reduced, you would always be taking the reduced version. Since it didn't reduce, it doesn't matter. Do I want to set this one equal to 0 or do I want to set that one equal to 0? Sometimes it's easier to work with the multiplied out one, and sometimes it's easier to work with the factored one. All right, I'm going to take the factored one. X plus 3 times x minus 3 over 2 times x minus 2, set it equal to 0, cross multiply. When we cross multiply, it's always going to end up that it's the numerator that ends up getting set equal to 0. X plus 3 times x minus 3 times 1 equals 0 times all that is 0. So now we set these equal to 0 and we find out that we have an x-intercept at negative 3 and we have an x-intercept at positive 3. Throw them on the graph as soon as you get them. Positive 3, it's crossing over the x-axis. Now guys, that's a clue. You now know that there is a point that your curve has to pass through in this bottom right box. You now know the curve is not up here, it's down here. That's a clue. All right, and then negative 3. This is a clue. You now know that there's no curve down here in this box. It's up here in that box. All right, let's get our y-intercept. To get the y-intercept, like always, plug 0 in, see what number comes out. Find f of 0. When you plug 0 in, you're going to get negative 9 over negative 4, which is what, 2 1/4? So now x is 2 1/4. That's just another clue showing that the curve is definitely up in this top left box. Okay, once you've done your intercepts, then after that, it's up to you to decide, do you have enough information to fill these curves in, or do I want to plug x's in as test points to create more points that our curve has to pass through? So the last step, step 7, is test points. And this is a personal choice. How many do you need until you are confident that you know what the graph looks like? So I always pick numbers to the left and the right of a VA. So in this case, maybe you want to plug in positive 1. I already know what happens when x is 0. Maybe you want to plug in x is negative 1 to create a point here. Maybe you want to plug in x is negative 2 to find a point there. Maybe you want to plug in negative 4 or negative 5 or negative 6. It's up to you what you need to do to create these points. Those might be some helpful things to do. All right, maybe you already know what's happening when x is, 3, maybe plug in 4, maybe plug in 5, maybe plug in 6, maybe plug in 2.5 to figure out what's happening right before that x-intercept. It's up to you until you figure out how many points you need to get a legit picture of this graph. I know this. I know that if a curve is on the right side of this VA, he ain't crossing over. I already know it's not crossing up into this one, so I automatically know that this graph has to follow this asymptote down to negative infinity because it can't cross over it. And then it's going to keep going. And like I said, these asymptotes are like magnets. The curves are drawn towards them. And then that one's going to follow it off all the way off to infinity. This one, right? If this had odd multiplicity, if this end of the graph goes off to negative infinity, then on this side, the graph has to go off to positive infinity. It also has to pass through these 2 points. So from left to right, I know it's going to go from here to there, and then it's going to shoot off to positive infinity. And then on this side, from right to left, it's going to go from this point to this point, and then it's going to have to follow that asymptote all the way out. But again, if you can't visually put that together, then you just have to keep plugging in x's to create ordered pairs to put on your graph. Does that make sense? Okay? Guys at home, are we okay? All right, perfect. Go ahead, Michael.
And it's a lot easier to visualize this because there are no crosses.
Exactly. Now, when there's a cross, Michael, 90% of the time, like, Michael, let's pretend you found out that it crossed the oblique asymptote when x was -4. So you would put a dot right on the oblique asymptote when x is -4. Normally, what it would do is it would cross over, and then it would just stay close to that asymptote on the other side of it, because an asymptote is a magnet. The graph is going to be drawn towards it and follow it off to the infinity. However, every now and again, you'll get a weird asymptote that, yeah, crosses over. Maybe it dips down a little bit, but it's always going to come back up at some point to follow that asymptote. So who cares if it dips? All we really ultimately care about is that this curve is on this side of the asymptote from x is -3 and or -4 and on. So again, even if it dips a little bit, it doesn't matter. All you should be showing is that after a cross, it's still going to follow that asymptote on the other side of it off to the infinities. Okay?
Yeah.
All right, perfect. All right, I'm going to try and do one more with you. I wanted to do another OA, but I haven't done one with you that you guys have seen an actual whole on and a reducing. So I want to do one more like that for you, and it's kind of quick. So let's see if I can get that one in, and then we'll call it a day with those two. And again, just while I'm erasing, you have a new homework assignment, but none of your homework is due until Friday. So you can kind of go in and out of each assignment, the more graphs that you see. I'm going to try and get your study plan up today. That way you'll have the whole week till Monday to work on that. And I'll keep the mastery points low for you guys. I get it. I know it's a lot of work. All right, let's try this one. Let's see a whole. Okay, step one, like always, FDR, factor, domain, reduce. Let's do that. Let's factor it. Now guys, I love canceling. It's my favorite part, but you really got to restrain yourself. Do not cancel anything until you have found the domain. So in this case, the bad guys that make my bottom equal 0 are -2 and +2. So those are our domains. Those are numbers we do not want to plug in. Okay. Now, once you've established who the bad guys are, then you're allowed to reduce your function. So in this case, a factor of x minus 2 and a factor of x minus 2, they're going to cancel. And that's going to leave you with a new function, 2x minus 1 over x plus 2. Circle it, star it, highlight it, whatever you need to do. There should be no reason to have to use the original function once it reduces. You should be able to use the reduced version for the entire rest of the problem and never have to go back. Now, sometimes when you reduce it, let's say there was like another factor left somewhere, maybe you have to multiply those factors back together to make this an easier version to use in the future, but you never have to go back to the beginning. You can use the reduced version from here on out. All right, let's go for it. Let's get our VAs. So now, look at your reduced version. In the reduced version, what x is the only x that looks bad now? Now, -2 is the only number who looks bad for this function. But 2 will always be bad. He will never be bad because we know where this function started. But -2 is the only one that still looks bad. So he's your VA, the one that still looks bad. Okay, so let's put it on our graph. Okay, all right, now let's get our horizontal or our oblique. Well, guys, if you look at the reduced version, I have a degree 1 polynomial over a degree 1 polynomial. According to horizontal asymptote rule number 2, you will have an HA, not an OA. And that HA will be the ratio of the leading coefficients. When the degrees are the same, it's like everything else in the problem cancels out, and you're just focusing on 2x squared divided by x squared. And then the x squareds will cancel, and you'll be left with 2 over 1. So you'll be left with an HA, no OA, and it'll be the line of y equals the ratio of the leading coefficients, 2 over 1, which is 2. So you'll have an HA at the line, y equals 2. Now throw that on your graph. So right now, I know there's going to be a curve to the left of this VA. Is it in the top box? Is it in the bottom box? Does it cross over and it's in both? I know there's going to be a curve to the right. Is it in the top box? Is it in the bottom box? Does it cross over and is it in both? These are things we're going to have to figure out. All right, now we're going to go to C. Let's see if it crosses. It's my least favorite step. Does it cross the HA? You have to take the reduced function on this step. If you don't take the reduced function, you can create a false cross at a hole. So take the reduced version, which is easier to work with, 2x minus 1 over x plus 2, and set it equal to whatever number the HA was at. It was at 2. Is this function ever going to equal 2? Cross multiply. I'm going to get 2x minus 1 equals 2x plus 4. Now solve for x. Solve for an x value that it could cross at. When you start solving, your 2x's are going to cancel, and you're left with -1 equaling 4, which is a false statement, which means good for us, no cross. That means everything is staying in their own box. The curve is either up here or down there, but not both. It's either up here or down there, but not both. All right, now we can go after some legit points. All right, let's go after a hole. This would be step 5. You only get a hole when a factor canceled out. So guys, I erased it, but there used to be an x plus 2 and an x minus 2. Only the x plus 2 factor survived. The x minus 2 canceled. So you take that cancel factor, set it equal to 0, and you get x equals 2, right? That's a bad guy. We know 2 is not in the domain. So since 2 doesn't look bad anymore, he becomes a hole, not a VA. But a hole, guys, is a point. It needs an x coordinate and a y coordinate. The x coordinate of our hole is clearly 2. What's the y coordinate? You got to plug 2 in and see what number comes out. So if I plug 2 in, plug it into the reduced version. There's no reason to go back. That's 2 times 2 minus 1 over 2 plus 2. That's 3/4. So you have a hole at the point 2, 3/4. So a hole is a point that your graph is going to pass through. It just your graph actually doesn't exist at that one point. So go to the point 2, 3/4 and put an open circle. It's a clue. We now know, guess what? The right curve is in the bottom box, not the top box, because that's a clue. That's a point that our curve has to pass through. All right, now let's get some other legit points, some intercepts. All right, take the function, the reduced version, set it equal to 0 and solve. But again, once you cross multiply, it's really just the numerator that ends up getting set equal to 0. And then you solve and you find out x equals 1/2. So it'll cross the x-axis at 1/2. So again, it's just further showing there is so a curve happening in this bottom right box. All right, let's get the y-intercept. Plug in 0, see who comes out. I plug 0 in, I'm getting -1/2. So now I know my y-intercept is -1/2. So again, there's so a curve happening right there. All right, after your intercepts, it's about what you need to do to finish this graph. So now you can go to test points, and now you can plug in whatever x values you want that are going to help you complete the picture. So I'm going to give you a clue. If you have no idea what's going on over here, if it's up here or down there, then maybe you should plug in -3, -4, -5. All right, if you want to plug in -1 to figure out what's going on when x is -1, have at it. If you want to plug in, when x is, 1, 2, 3, or 4, or 5, you do what you got to do. I already know that my curve has to do this. He's got to pass through those 3 points, right? And then what's it going to do? It's going to follow the momentum as it comes through this hole, and it's going to shoot towards that asymptote and not cross. I know it can't come back down. It has no other x-intercepts. And then from right to left, it's going to go from the hole to this dot, and then what's it going to do? It's going to follow that asymptote all the way out. Now remember, this asymptote, x equals -2, it only couldn't be it one time. So it had odd multiplicity, which means if this side of the graph is shooting off to -infinity, this side has to shoot off to +infinity. And now I know this curve is in my top box doing that, not my bottom box. I also know it couldn't possibly be in the bottom box because if it was in the bottom box, I would need another x-intercept, and it doesn't have another x-intercept. So that means it has to be in the top box as well. But again, if you have trouble visualizing these curves, then guys, you just got to plug x's in until you get enough points. Okay? How does that one feel? Everybody okay? Good? Case, how are you? All right? Okay. All right. Woo! That's a workout. All right, so guys, we have 1 minute left. So I did create another homework for today. I think today's has 5 graphs in it. Tomorrow will probably be the last homework that I assign, and then it will just be homeworks and study plan until the rest of the week. Please reach out to me if you need any help or extra help. I can meet you in the afternoon. I can do graphs with you, whatever you need to do. Just please let me know if I can